Hi, everybody. I hope you had a good night. A little bit more on simple harmonic motion. And just a quick apology. For some odd reason, I'm not sure exactly why. I think got too many slides last time. There's no brain break today. But I'll make sure I'll have one next time. So it's a relatively short presentation, not a lot of slides, but some animations. So simple harmonic motion so far. For a mass in the spring, we've noticed that the period and frequency does not depend on the amplitude. That's one of the requirements for simple harmonic motion. And we'll see it's true for all of the cases of simple harmonic motion. And oscillation occurs around the equilibrium point, and at the equilibrium point, the net force is actually zero. But that's the point where there's maximum velocity. We have these three equations that give us the position, velocity, and acceleration of a simple harmonic oscillator at any given time. The one thing I want to mention just real quick in passing is this. Does it have to start out, for example, a cosine curve is a maximum at t equals 0. Does it have to start out a maximum? The answer is no, and for some of you in math, you might know that you can add, inside of here, a term like plus phi or phi, where this is the offset. That would shift the wave either left or right, depending on how large phi is. And so you can add that to each one of these. It doesn't change the rest of the formula, but it does offset these by some amount. The other thing I want to mention real quick is we derived this equation last time. So these three equations give you position, velocity, and acceleration with respect to time. This gives you the velocity with respect to x, so you can plug in any value x and figure out what the velocity is at that instant. And this one gives you the acceleration for any position x. So for any displacement, you know the velocity and the acceleration, where k is the spring constant, m is the mass, and capital A is the amplitude. That's the maximum displacement of the object. From those, we were able to derive these two equations for a mass spring oscillator last time. The period of a mass spring oscillator is 2 pi times the square root of its mass over the spring constant. Or since remember frequency is the reciprocal of period, you can also write as 1 over 2 pi times the square root of k over m, where this is the frequency, number of oscillations per second of one of those things. So the question is the simple pendulum. And by this point, I'm hoping most of you had a chance to try out the lab, because otherwise I'm about to give you a few spoilers. The question is, how do you solve it? Now take a quick look at it before we get going here. Notice the restoring force is this component of gravity that acts along the slope right here. And you get a maximum restoring force when it's at a maximum displacement. And the displacement, x here, is actually this arc length that's along this point here. It's not a straight line path this time. So how do we solve this? Oh, before I get there, I've got to do a small sidebar. Remember, sidebar, I'm taking you away from the notes for a brief moment. Some of you have done Taylor expansions. Yes, all grown in unison. I know most people hate them. You're like, no, not Taylor expansions. Well, this is how your Inspire actually calculates the sine and cosine functions. It actually does this expansion. It's an infinite series. Sine of theta is equal to, this has to be in radians, is equal to theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial, yada, 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 alternating signs each time. And cosine of theta is equal to 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial plus, you got the idea. But my question is, what happens for theta that's much less than 1? That's what the double less than signs mean. Well, these terms in the back here get very small. Sorry, white on white. And you end up with this situation where the sine, for all practical purposes, is about theta. And cosine is about 1, which means that tangent of theta is about theta. So remember, tangent sine over cosine, theta over 1 becomes just theta. And you might say, well, wait a second, Mr. Clemmer, why are you doing this? Well, trust me for a brief moment. Let me show you. So let's take a look at a simple pendulum. So here we've got a simple pendulum of length L. It's moved over some angle theta, and we've got the force of gravity mg acting on it. So the first question is what's the restoring force? You're like, oh, mg. Well, Oh, that's funny. Um, mg, not, yeah, OOH. Um, in reality, though, it's only a component of this force of gravity, the component that's acting along this arc length. And my apologies, I couldn't draw a nice arc. That's supposed to be an arc, not a straight line. And what is that going to be equal to? Well, this angle right here is theta again. And so this side of this triangle is equal to mg sine theta. This side would be mg cosine theta, but this is the one I'm interested in because this right here is my restoring force. So my restoring force is mg sine theta. And what's the displacement? The arc length. And let me draw it better this time than I could do with the Microsoft tools. This arc length right here, if you remember from Alg 2, is just equal to the radius of your circle times theta in radians. And remember, we're working in radians in all of these. And so the arc length is just equal to L times theta, where L is the length of this pendulum. So if this, we know this system exhibits simple harmonic motion, what's its equivalent of a spring constant, K? Well, remember that everything that exhibits simple harmonic motion has to obey Hooke's law. There has to be a restoring force. If we plug in what we know, so up here we've got this force, and down here we have this displacement. If we plug those two in, sorry, my pen is lagging, we should be able to solve this. And remember, and now here's the critical part. This equation down here is not very pretty, but remember that for small thetas, sine of theta is about theta. So what I'm going to do here, and it's going to drive some of you crazy, is I'm going to say sine theta is approximately equal to theta. You're like, what? Yeah, no, I know it's an approximation, but it makes this very simple. This now becomes this, and our K for a pendulum is mg over L. But now we still have the question of what's its period? Well, we know that the period of a mass spring oscillator is given by this. We solved this earlier. So what happens if we plug in this for our spring constant K in this equation? Well, we get this, but you'll notice that the mass cancels. And you end up simply with this. So here it is, the period of a simple pendulum, where you just have a mass in the end of a massless string, it's just given by 2 pi times the square root of the length over gravity. So the thing that really affects the period is the length and the gravity of the planet you happen to be on. Well, for Earth, most of the time that's g. But just a really quick note, prospectors in the American West used to use a grandfather clock to prospect, that is, search for metals, like gold in particular. And you might say, how in the world would that work? Well, here's what they did. Before they would go to bed each night, they would set their pocket watch and a pendulum clock, grandfather type clock, to the exact same time. So here's a little pocket watch. They'd set it to the exact same time. Let's make it midnight. And their grandfather clock exactly to the same time, midnight. And then they would sleep, go to sleep, and wake up the next morning. Now, if the grandfather clock ran faster than their watch, they may actually put a little flag there and say, yeah, this might be a good spot. Now you might say, wait, what's going on? Well, above a mineral deposit, remember metals are usually much more dense than other materials? It makes G ever so slightly larger up above those areas. It wouldn't affect the little stopwatch because that just is a mass spring oscillator, but it did affect the grandfather clock or grandmother clock. If G was larger, what would that do to the period? It would actually make it run with a smaller period or a higher frequency. This would swing back and forth faster. Did I just say it backwards before? I think I might have. So if this actually ran fast is when you would put a prospector flag on there because G was bigger than normal. And that meant you might be above a mineral deposit. Cool. So you're sitting on a swing, a friend gives you a small push, and you start swinging back and forth with a period of T1. Suppose you are now standing on the same swing rather than sitting. When given a small push, you start swinging back and forth with a new period, t2. Which of the following is true? Is t1 going to be equal to t2? Is t1 going to be larger than t2? Is t1 going to be smaller than t2? Think about it for just a brief moment, and I'm going to give you the answer in 3, 2, 1. The answer is the length of your pendulum is measured from the pivot point to the center of mass. And if you're sitting, center mass, remember, near your belly button. If you're standing, that's going to be up here, and so the length becomes smaller. So the smaller length means that your second period, the period when you're standing, is going to be smaller than when you were sitting, because you basically shortened your pendulum. Take another look at this one. You're on a distant, it's supposed to be distant planet, not distance planet, with the string mass and stopwatch. You need to calculate the acceleration of gravity on the new planet. So how do you do it? Well, you hang it down. So your length of your pendulum is 1 meter, and you measure the period at 1.8 seconds. What's the acceleration of gravity on this planet? Well, you can very quickly calculate it just by using our new equation. Our period 1.8 equals 2 pi times the square root of 1 over g. Oh gosh, should I solve it in a different way? Yeah, let's go do this. So 1.8 squared over 4 pi squared is equal to 1 over g. So if you solve this real quick, I'm going to grab my calculator and do this. And I get g is about 12.2 meters per second squared on this new planet. That's supposed to be a meter. There we go. I think I got that right. Yep. Good. All right. How do the position, velocity, and acceleration of a simple harmonic oscillator vary? Well, remember there are sinusoidal functions. The question is, when does it have a maximum velocity? And that is when x is equal to 0, when it's at its equilibrium position. When does it have a maximum acceleration or a greatest restoring force acting on it? And that would be when x is equal to the amplitude, when it's at its maximum displacement. Mathematically, we can actually sort of look at it. If we graph this real quick, and I'm going to do this manually here. Whoops, dink, dink. Here's a pendulum swinging back and forth, and I label the positions all the way through here. And let's make this side positive and this side negative. Its maximum position is when it's at point A. And we know this is going to be sort of, I'm going to make it as a cosine function. I'm going to go shoot 4 around through here. Going down 3 here. Going back, whoops, 2, 2, 2. Sorry, I think my way through here. Whoops, I went too quick. 2, 2, shoo, 2. What would this point be right here? This is point D. What's this point down here? This is point G. This is back to D. Back to A, back to D. Make my A better. Oh, my chord's right in the way. Sorry. Back to A. I'm like, why is this not writing? And back down to G. Please forgive my relatively bad graph. But now the question is, what's the velocity? Well, when's the velocity a maximum? Well, the velocity is a maximum when we're at the equilibrium position. So the first time I come back from A back to D, I've got a very large negative velocity. So at point D here at this time, I would be a negative velocity. And at this point right here, when I was at A, my velocity should be 0. And so what kind of graph, and this time I'm going to draw mine a little bit better. I stop again there. I end up with a graph that looks like this. So at point D is when I have a maximum. Point A here, I'm at 0. Point G, I'm back at 0. This lines up with that one. And then back over here at D. I'm back. This time I'm now swinging back here. I have a maximum positive as I swing back from this point. And you'll notice that, oh yeah, whoops, sorry, ooh, horrible, sorry. Back at A, back down here at D, and then back over here again at G. What graph is this? You might realize this is a negative sine graph. This one up here was a cosine graph. Make sure I did that right. Moves from A back to D. Get a maximum negative. Yeah, it should be right. And then finally, what's my acceleration graph going to look like? It's going to be something that looks like this. I get when I start right here, I get a maximum negative acceleration when it's at point A. And that's going to drop back to 0 by the time I'm back here at D. What's this one going to look like? It's going to look like this, where this point here is G again. This is a negative cosine curve. And if you double check, that's exactly what we were expecting. Oh, sorry for that line. If you take a look at our original functions that describe the position, velocity, and acceleration with respect to time, they're cosine, negative sine, and negative cosine graphs. But now you can visualize it. The amplitudes of these are not the same. If you take a look at the original equations. What's it look like? It looks like this, and you can sort of see the acceleration where he did it. What types of energy does a mass spring oscillator have? And the answer is kinetic energy and elastic potential energy. When's at each type of maximum? When does it have maximum EPE? Well, when it's either when x is equal to, oh my goodness, sorry, negative amplitude, or x is equal to the positive amplitude. That's when EPE is max. When does it have maximum kinetic energy? Think about it. It'd be the point where it has maximum velocity. Sorry, I gotta switch my pen color. Kinetic energy is going to be a maximum when it's at its equilibrium point. In other words, when x is equal to 0. All right. Sorry, I've got the equations on there. All right, now we get to move into waves. Yay, waves are fun. So what are waves? Waves transfer energy without the net transfer of mass. Here's an ocean wave real quick, and this little black dot is following a little bit of the water as a wave passes by. As the wave goes by, that matter actually just travels in a circular path. You may have seen this before if you've seen like a cup or something sitting in waves where there's no wind. You'll actually see that it kind of goes up and down in this sort of circular path without a net motion. If you have a bunch of waves, you can sort of see this. Each little mass oscillates, and it transfers energy to its neighboring matters, both in 2 dimensions shown here, but also in 3 dimensions along this line. And so these are kind of fun to see waves. Waves are a great way of transferring motion or energy from one point to another. So types of waves. We're going to talk about 2 different types of waves. Longitudinal waves are where the wave motion transfers along this way, but the source is moving up and down. The matter at each point goes up and down as it goes through here. And then a longitudinal wave where you transfer energy this way, and the matter in it moves back and forth this way. So transverse waves, oscillations are transverse or perpendicular to the direction of motion. Longitudinal, or sometimes called the compressional wave, oscillations in the direction of motion are parallel to direction of motion. And down here is an animation of a bunch of mass springs connected together where you suddenly push one, and that compression travels along it. This would be a longitudinal wave. There's also, we need to talk about this real quick. There's different, every wave can either be pulse, where you got just a single wave crest or trough, or it can be continuous, where you've got a repetition of those constantly moving through it. The velocity of a longitudinal wave is just the tension divided by mu, where mu is the mass per unit length, how many kilograms per meter you have. For these kind of waves, we'll talk a little bit more. In general, waves have a very simple formula. Oh, I've got to show you this real quick. This is students demonstrating a wave. Down here, they're demonstrating a longitudinal wave where the compressions are moving along this way. And if I can get this one going up on top here, I may have to turn off the pen briefly. Oh, there they go. And up here, they're demonstrating a transverse wave, where the oscillations are perpendicular to the direction of motion. And this is actually a pretty good simulation. They're really good at this, I have to admit it. I wonder how long they practice, but I'm super impressed. Why am I impressed? After one of my physics classes watched this one, they're like, hey, we can do better. I'm like, yeah, let's see. So here it is, transverse wave Concordia style, where each student is trying to move up and down one of the blocks outside near the track each time that we beep. And you see, we did pretty well. A few people got out of sync. But you can sort of see, and this was after the first practice, so yeah, it was not perfect, but it was still pretty fun. Okay, moving on. Wave speed or velocity. The more general equation is the wave speed equation. Most of you learned this back in chemistry, where F stands for frequency. This is the Greek letter lambda. It stands for wavelength. And V is the velocity in meters per second. Wavelength can be measured from crest to crest. It can also be measured from trough to trough, or it can be measured from any point, in this case going down from the equilibrium point, going down from the equilibrium point. The distance between these 2 points would also be the wavelength. So any point where it's about to repeat its motion, the distance between those is the wavelength. Warning, this is a graph of amplitude versus, or position versus, let's call it amplitude, versus distance x. It sometimes gets confusing for some students. You'll see graphs like this where this axis is time. Then the distance between this would be the period, the time required for it to go through one oscillation. Because this is distance, this is the length in meters between repetition. So amplitude, again, from equilibrium point either to a crest or from equilibrium down to a trough is the actual amplitude. The wave velocity depends on the medium through which it moves. So there's a nice... So notice what happens in here. This is the PhET wave simulation, and I just want to show you, I'm going to turn this on so it starts dripping. There we go. The velocity of the waves depend only on the medium. In this case, it stays constant. But take a look at this. You'll see that the waves move over with a certain wavelength, distance between the crests or the troughs. Notice what happens if I increase the frequency. I'll take it all the way up to max here. It may look like the waves are moving faster than before, but they're not. The velocity across the screen, you can time it, is the same as before. But what's happening here at the higher frequency, the wavelength, the distance between the crests or the distance between the troughs, is getting smaller. And maybe this is more obvious if I take the frequency down to the smallest possible. It's pretty low. The wavelength now becomes crazy long. So as frequency decreases, wavelength increases, and the reverse of that's also true. As you increase frequency, wavelength decreases. Again, the velocity of these waves are the same as they were before. So hopefully you get a chance. There's the last couple of slides. That wave simulator is linked to the assignment sheet. It's fun to play with, trust me. So take a look at these questions. I just want to go through them with you real quick. Rhonda sends a pulse along the rope. How does the position of the point of the rope before the pulse comes compare to its position after the pulse has passed? The answer is the same. Remember, waves don't move matter, they just transfer energy. Why don't incoming ocean waves bring more water to the shore until the beach is completely submerged? Because, again, there's no net motion of the mass. In order for a medium to be able to support a wave, the particles in the wave must be frictionless, isolated from each other, able to interact, or very light. Correct answer is, of course, they must be able to interact with each other. A transverse wave is transporting energy from east to west. How will the particles of the medium move? And the answer is they have to be perpendicular to that, so they'll be moving north and south. A wave is transferring energy from left to right. The particles in the medium are moving back and forth in the left and rightward direction. This type of wave is known as a longitudinal wave. Good. In the diagram above, the wavelength is given by which letter or letters? The answer is, in this one, has to be A. The amplitude is given by what letter? That would be D, or it would actually be half of B. They don't give us that option. 8. A wave has an amplitude of 2 centimeters and a frequency of 12 hertz, and the distance from a crest to the nearest trough is measured. That determine the period of such a wave. And you're like, whoa, 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 whoa. Lots of extra information. The only thing we need to know on this one is the frequency. Remember, period is 1 over the frequency, the reciprocals of each other. So it's just 1 over 12 hertz, or 1/12 of a second. A tennis coach paces back and forth along the sidelines 10 times in 2 minutes. The frequency of her pacing, that's the number of oscillations per second, would be 10 oscillations in 120 seconds, or reducing that 1/12 of a hertz. A pendulum makes 40 vibrations in 20 seconds. What's its period? In other words, how long does it take to make one vibration? Well, it would be, if we do 40 in 20 seconds, that 20 seconds, there's 40 of them. How long does it take for just one of them? Well, 20 over 40, or a half of a second. Mac and Tosh are resting in the top of the water near the end of the pool. When Mac creates a surface wave, the wave travels the length of the pool and back in 25 seconds. The pool is 25 meters long. Determine the speed. Velocity is just distance over time. In this case, goes a total distance of 50 meters. In 25 seconds, its velocity must be 2 meters per second. Finally, a marine weather station reports waves along the shore that are 2 meters high, 8 meters long, and reach the second 8 seconds apart. So this would be the period. 8 meters long must be the wavelength. Determine the frequency and speed of these waves. Frequency, just 1 over the period, so that's going to be 1 over 8 seconds. Velocity, frequency times wavelength. We know the frequency is 1/8 of a second, 1/8 hertz. Wavelength is 8, so the velocity must be 1 meter per second. Good luck. You should be all set for your wave questions tonight for homework. Have a great night, and please talk to me during office hours, even though I forgot to do them the other day. Hopefully we'll see you today. Have a good night. Talk to you soon.